Welcome everyone, and thank you for joining this session on database testing using SQL. My name is Joglu Sarwar, and I'll be guiding you through the key concepts and techniques involved in testing databases effectively with SQL queries. Throughout this presentation, we'll explore how to ensure data integrity, validate stored procedures, and check for performance issues, all using practical examples. Whether you're new to database testing or looking to sharpen your skills, this session aims to provide clear and useful information to help you confidently work with databases in your projects. Let's get started. A database is essentially an organized system created to store, manage, and retrieve information efficiently. It includes both physical components, like data files and hardware, and logical structures, such as tables and indexes, which help organize the data. There are several popular database systems we often work with, including MySQL, Microsoft SQL Server, Oracle, and IBM's DB2. Each of these platforms provides robust tools to handle data in different environments, but they all serve the core purpose of making data accessible and manageable. Understanding these databases helps us ensure the integrity and quality of data during testing. When testing databases, it's important to focus on several key areas to ensure everything works as expected. First, we look at the database schema, which includes tables, columns, their types, default values, and rules that apply to them. We also verify keys and indexes, along with stored procedures and triggers that automate certain operations. Testing integration between the schema and the overall system is crucial to check that data flows smoothly and functions operate correctly. We check functions and features for correctness, as well as data integrity and consistency to avoid corruption or loss. Security measures like login and user privileges, database access control, and table-level permissions are tested to protect sensitive information. We also pay attention to file paths for data sources and destinations, handling of variables and batch processes, and how source and destination files are named and managed. Error levels and messages are monitored for proper handling of exceptions. Finally, we validate data download, conversion, and distribution processes to ensure reliable data movement and transformation in the system. This comprehensive approach helps maintain a robust and secure database environment. User interface testing focuses on how users interact with the system's front end. It checks elements like text boxes, drop-down menus, calendars, hyperlinks, buttons, radio buttons, images, and overall layout to ensure they work correctly and are user-friendly. On the other hand, database testing examines the interaction between the system and the database itself. This includes verifying database objects such as tables, columns, indexes, sequences, views, stored procedures, and triggers. While UI testing ensures that the system's interface behaves as expected from the user's perspective, database testing validates the integrity and functionality of the data and its structure behind the scenes. Both types of testing are essential to delivering a reliable application, since they focus on different layers but ultimately contribute to a seamless user experience. Before beginning database testing, it's important to thoroughly review several key components. Start by examining the front-end or client layer, including the graphical user interface, to understand how users interact with the system. Next, review the business logic layer, which processes user inputs and controls data flow. Take a close look at the entity relationship diagrams to understand the data model and how different entities connect. Then, focus on the database design itself, ensuring it meets the required standards and structure. It's also essential to review the internal components like tables, views, and stored procedures, since these directly affect data retrieval and manipulation. Finally, looking at data flow charts helps identify how data moves through the system, which can highlight potential points of failure or bottlenecks. This comprehensive review process helps ensure that testing will cover all relevant areas effectively. The basic layer of any application, we have the client or user interacting with a graphical user interface. This interface communicates with the database server, which handles data storage, management, and retrieval. The database server processes requests from the client, executes queries, and returns the necessary data. This interaction forms the foundation for testing both the user interface and the underlying database to ensure they work together correctly. Understanding how these two layers connect is essential when reviewing and validating the system. so you can accurately test data flow and functionality from the user's actions all the way to the database responses. In this section, I want to emphasize the connection between the user interface, the business logic, data access, and the database itself. These layers work together to deliver a seamless experience for users while managing data efficiently behind the scenes. The user interface interacts with the business logic, which processes the rules and workflows. Then, the data access layer communicates with the database to store and retrieve the necessary information. Understanding this flow helps ensure proper testing and validation across all parts, from what the user sees to how the data is handled, guaranteeing the system functions reliably and accurately. This diagram shows how the course registration process works by breaking it down into two main steps. First, the system checks whether the course is available by sending an inquiry to the course database and receiving a reply about availability. Once the course availability is confirmed, the system then checks the applicant's qualifications by querying the application records. Finally, based on these checks, the system either accepts or declines the enrollment request back to the external entity, which could be a student or user submitting the application. This clear flow ensures that each application goes through a structured validation of both the course and the applicant before final enrollment decisions are made. Here, we are looking at a simple SQL query used for integration testing in the database layer. The query selects all columns from the user AC table, where the accounted matches 10,024. This is a straightforward way to verify that the data for a specific user is stored correctly and can be retrieved as expected. By executing such queries, we ensure that data entered through the interface or business layer flows accurately into the database. You can see the table structure includes fields like first name, last name, email, passwords, zip code, and phone, which represent typical user account details. This approach is vital for confirming that the back-end data aligns with what the system's front end submits, helping catch any mismatches early in the integration testing process. Data corruption often happens because of poor design choices in the database. For example, redundant data can cause issues like when the same customer is entered twice, but with different primary keys, making it hard to track correctly. Inconsistent data is another problem, especially when multiple applications add records to the same database without coordinated rules, leading to mismatches or conflicting information. Additionally, validating business rules in both the database and the client side without proper coordination can cause conflicts or errors, which we call redundant validation. These problems highlight why thorough database testing is crucial. Without testing, these kinds of data issues can go unnoticed and impact the overall reliability of the system. A relational database management system, or RDBMs, is a collection of programs designed to help users create and manage databases efficiently. It forms the foundation for SQL and is used in many modern database systems such as MS SQL Server, IBM DB2, Oracle, MySQL, and Microsoft Access. One important concept in database design is normalization. This technique organizes data by breaking down larger tables into smaller, related tables to reduce redundancy and dependency. By linking these smaller tables through relationships, normalization helps maintain data integrity and avoid issues like data duplication or inconsistency. In the diagram, you can see how data is organized into separate tables like product, customer, and order, each linked by keys to keep the information structured and easy to manage. This kind of planning is essential for creating efficient, reliable databases that support specific applications while minimizing potential errors. SQL, which stands for Structured Query Language, is widely used as the standard language for working with relational databases. Most implementations follow the ANSI standard, which ensures consistency across different database systems. SQL lets us retrieve data, manipulate it, and manage databases efficiently. One important use of SQL is in database testing, where we use specific statements to verify that the data and operations behave as expected. The language is very flexible. There are no strict rules about how to format or break lines, which makes it easier to write and read SQL statements according to your preferences. This flexibility, combined with its powerful data handling capabilities, is why SQL remains the go-to language for database work in many modern applications. Let's take a closer look at the basic structure of an SQL query. An SQL query usually follows a simple format that starts with a command like select, which tells the database what data to retrieve. This is followed by specifying the columns or fields you want to see, then the table from which to pull the data. You can also include conditions to filter the results, using the where clause, and even sort data or group it if needed. Understanding this straightforward structure is key to effectively accessing and manipulating data in any relational database. When working with databases, we use query statements to retrieve data stored in tables, and the most common way to do this is with the SQL select statement, which lets us pull data efficiently. But beyond just getting data, SQL includes data manipulation language statements that allow us to change the data inside tables. There are three main DML commands: insert, which adds new rows of data to a table; update, which modifies existing data in the rows; and delete, which removes rows from the table. In many testing scenarios, testers typically have permission to execute select statements to view data, but sometimes they need to request update permissions if they are allowed to change data in the database for certain test cases. Understanding these basic commands is key because they form the foundation of how we interact with and manage database information during testing and everyday operations. Data definition language, or DDL, statements are used to define and manage the structure of a database. There are 5 main types of DDL statements. First, create is used to create database objects like tables or users. Alter lets you modify the structure of an existing database object, such as changing a table. Drop removes database objects, like deleting a table. Rename allows you to change the name of a table. And truncate removes all the data inside a table but keeps the table itself intact. It's important to note that testers typically don't have permission to run these DDL statements, as they can greatly alter the database structure. These commands are fundamental in setting up or maintaining the database framework before manipulating the data within it. Transaction Control Language, or TCL, helps us manage changes made to the data in a database. There are 3 important statements in TCL we use to control these transactions. The commit statement makes any changes permanent, saving the records to the table. If we decide we don't want to keep those changes, we use rollback to undo them, returning the data to its previous state. SavePoint acts like a bookmark within a transaction, letting us set a point we can revert to without affecting earlier changes. These tools ensure we can save, undo, or partially revert changes, giving us precise control over how data is stored and maintained in the database. In SQL, Data Control Language, or DCL, is used to manage permissions on database structures. There are 2 main statements in DCL: grant and revoke. The grant statement allows one user to give another user access to certain parts of the database, such as tables or views. On the other hand, the revoke statement is used to remove or prevent access that was previously given to a user. These statements are important for controlling who can see or modify data, and typically the database administration team is responsible for handling these permissions to maintain security and proper access control within the database. A table in a database organizes related data into columns and rows. Each column represents a field, which defines a specific type of data stored in the table. For example, in a customer's table, fields might include ID, name, age, address, and salary. Each row, or record, is an individual entry that holds values for each field, representing one unit of data within the table. Meanwhile, columns specify the data type and define what kind of information will be stored in each field, ensuring the structure is consistent and meaningful. This structured format helps to efficiently store, retrieve, and manage data within a database. Primary key in a relational database is a column that uniquely identifies each record in a table. This means every value in that column must be unique and cannot be null, ensuring that no 2 rows have the same primary key value. For example, in a student table, the student id serves as the primary key because it uniquely identifies each student. On the other hand, a foreign key is a column that establishes a link between 2 tables by referring to the primary key in another table. So, in this case, course ID is the primary key in the course table, but acts as a foreign key in the student table to create a relationship between these two tables. This setup helps maintain data integrity and enables easy navigation between related data in different tables using SQL. Here, you can see an example of how a key relationship works between two tables in a database. The top table shows student information with a unique primary key called student ID. Each student record includes other details like first name, last name, and course ID. The course ID acts as a foreign key that connects this table to another table below, which contains course details. In the course table, course ID is the primary key and uniquely identifies each course, while course name describes the course itself. This relationship ensures that each student is linked to the correct course by matching the course ID across both tables. This helps maintain data consistency and makes it easier to manage related data across tables. A primary key uniquely identifies each record in a table and must always have a unique value, with no nulls allowed. You can only have one primary key in a table, and its values cannot be changed once set. On the other hand, a foreign key is a field that links to a primary key in another table, helping maintain relationships between tables. Foreign keys can accept multiple null values, which means they don't always have to point to a record, but when they do, they ensure that the row in one table corresponds correctly to a row in the related table. This connection helps keep data consistent across the database by enforcing referential integrity. Normalization helps organize data by breaking down large tables into smaller, related tables. This process reduces redundancy and improves data integrity. There are different types of relationships used to link these tables, including one-to-one, where each record in one table corresponds to a single record in another table, one-to-many, or many-to-one, where a single record in one table relates to multiple records in another, and many-to-many, where multiple records in one table are associated with multiple records in another. Understanding these relationships is key to designing efficient and well-structured databases. In this example, we see a one-to-one relationship between the customer and address tables. Each customer has a unique customer ID, and each address entry has a corresponding address ID. The key point here is that every customer is linked to exactly one address, and each address belongs to only one customer. This structure helps keep the data organized and avoids duplication, as customer information and address details are stored in separate tables but connected through their IDs. This setup is common when you want to separate data into manageable pieces, while maintaining a clear relationship between them. Here we see an example of a one-to-many relationship between customers and their orders. Each customer is identified by a unique customer ID in the customer table, with names like Louise Lenny, Kenny Mark, and Roni Kim. On the other side, the orders table lists individual orders, each with an order ID, the related customer ID, the date of the order, and the amount spent. This setup shows how one customer can have multiple orders linking through the customer ID, which acts as a key connecting the two tables. This kind of relationship helps organize data efficiently, so we know which orders belong to which customer without duplicating customer details in every order record. Here we see an example of a many-to-many relationship in a database. The first table lists items, each identified by an item ID and linked to one or more orders through the order ID. Examples include a camera, phone, bike. The second table shows order details, including the order ID, customer ID, order date, and the amount spent. Because each order can contain multiple items, and each item can appear in multiple orders, this creates a many-to-many relationship. This type of relationship often requires an additional table, sometimes called a junction or associative table, to properly link items with orders in a normalized database. This setup ensures efficient organization and retrieval of data related to customers' purchases. In SQL, different types of functions help us work with data effectively. Aggregate functions return values calculated across multiple rows in a column, like count, sum, average, minimum, and maximum. Date and time functions let us extract or manipulate date and time values, for example, getting the current date or time. Numeric functions allow us to perform calculations such as rounding numbers or finding square roots. Character functions work with text and can combine strings, find string lengths, or replace null values. Conversion functions help transform data from one type to another, such as converting strings to numbers or dates. These functions make it easier to analyze and manipulate data directly within SQL queries. In SQL, null is a special value that represents missing or unknown data, and it's important to understand that it's not the same as an empty string or zero. When you want to find rows where a column has no value, you use the isNull clause. For example, if you want to select products where the color information is missing, you would write select from product where color is null. On the other hand, if you want to find products that do have a color specified, you use isNotNull in the where clause. This distinction is crucial when filtering data, as comparing with an empty string or using equality operators won't work the same way with null values. The examples here show how to query a table to find either known or unknown color values using these isNull and isNotNull conditions. In SQL, comparison operators help us filter data by comparing column values to specific criteria. For example, the greater than symbol allows us to select rows where a value is higher than a set number. Similarly, less than filters for values below a threshold. We can also use greater than or equal to and less than or equal to include values that meet or exceed certain limits. To find rows where a column does not equal a particular value, we use either the not equal symbol or the angle brackets combined with an equal sign. Additionally, using any lets us compare a value against any element within a list, returning rows that satisfy the condition for at least one item. On the other hand, all requires the value to satisfy the condition across every item in the list. These operators are crucial for crafting precise queries, especially when narrowing down results based on numeric or categorical data. The group by clause is used to organize rows that share the same value in one or more columns into groups. This allows us to perform operations on each group instead of individual rows. For example, you can specify multiple columns to group by, which means the rows will be grouped based on the combination of those column values. We often use aggregate functions like AVG, count, sum, or max along with group by to calculate summary statistics for each group. Additionally, the order by clause can be applied to sort the groups based on the result of an aggregate function or any column. The having clause is useful for filtering groups after aggregation, so you can include only the groups that meet certain conditions. In the example shown, the query selects the product ID and the average list price from the product table, groups the results by product ID, filters out groups where the average price is 20% or less, and finally orders the remaining groups by their average price. This makes it easier to analyze datasets by summarizing and refining results based on grouped criteria. The having clause is used to set conditions on groups of rows after they've been grouped by the group by clause. It works like a filter for groups, unlike where, which filters individual rows before grouping. When using where and group by together, the query first filters rows with where, then groups the remaining rows with group by, and finally applies any having conditions to those groups. For example, you can select products where the list price is less than 150, group them by product ID, and then use having to only keep groups where the average list price is greater than 20%. You can also use order by to sort the results by the average list price, which helps display the results in a meaningful order. This way, you control which rows enter the grouping, which groups are included, and how the final data is presented. The select clause is used to get data from tables in a database. When you use select followed by an asterisk, like select from sales order detail, it means you want to retrieve every column and row from that table. You don't have to get all the data, though. The where clause lets you narrow down what rows you want. For example, if you only want information about a specific product, you can add where product ID equal to 836 after the select statement. This way, you're telling the database to only return rows where the product ID is 836. The where clause is optional, but it's very helpful when you want to work with a subset of data instead of the entire table. In SQL, operators help us filter and match data in different ways. For example, The like operator lets us find patterns within strings, while not like excludes those patterns. In allows us to check if a value matches any item in a list, and not in does the opposite. Between helps us find values within a specific range, with not between excluding those ranges. When dealing with missing or special values, is null finds all null entries, and not is null finds records with actual values. Similarly, is nan identifies values that are not a number, and is infinite targets infinite double values, with the negative forms excluding those. These operators play a key role in crafting precise queries to get exactly the data you need from your tables. Here we use aggregate functions, which are often called group functions because they work on groups of rows. In this example, we're calculating 3 values for the list price column from the product table, the total sum of all prices, the total count of rows that have a price, and the average price. The sum function adds all the list prices together, showing us the total price of all products. The count function simply counts how many prices are listed, giving the total number of products. Lastly, the average function calculates the mean price of all the products. These functions are helpful in summarizing and analyzing group data efficiently. Here we see how the concat function works by combining 2 string values into one. In this example, it merges the first name and last name of customers from a table where the customer IDs are 1 and 2. The highlight here is that instead of returning 2 separate columns for the first and last names, concat combines these into a single string for each customer, like Orlando Gee and Keith Harris. This is useful when you want to create full names or other combined text fields easily in your query results. When working with a table like this employee list, we might want to get all the cities where the employees live, but without repeating any city more than once. Using the distinct keyword in our select statement helps us do exactly that. Instead of just selecting all employee locations, which could include duplicates, adding distinct ensures that each city appears only once in the result. For example, if we write select distinct employee location from employee, the output will show New York, India, Russia, and Canada each just one time, regardless of how many employees are from those places. This makes it easier to see the unique locations without any repeats. When working with databases, the SQL join clause allows you to combine rows from 2 or more tables by matching values in a common field they share. This is useful when you want to bring related data together, like linking customer details with their orders by using matching keys such as customer ID. There are different types of joins, but the core idea is to create a single, unified result set that pulls relevant information from multiple tables based on those shared fields. This makes it easier to analyze data that is stored across different sections of a database. The inner join keyword helps you combine rows from 2 tables, but only includes those where there is a matching value in both tables for the specified columns. This is useful when you want to see related data from both tables side by side, like matching customer orders with their customer details. The SQL syntax starts with select, followed by the columns you want, then from the first table, and inner join the second table using the on clause to specify which columns should match. The Venn diagram here shows this clearly by highlighting the overlapping area, meaning only the shared rows between the 2 tables are selected. This method ensures your results are precise, focusing on the data that exists in both places. The full outer join returns every row from both tables, matching them where possible, and including all rows even if there's no corresponding match in the other table. This means it combines the results of both left and right joins. The syntax for this join is straightforward. You select columns from the first table, then use full outer join with the second table, specifying the condition where the columns are matched. The Venn diagram here illustrates this by showing both circles fully included, representing all rows from both tables, with the overlap indicating matched records. This join is useful when you want a complete view of records from both tables, regardless of whether matches exist. A left join returns all the rows from the first table, which we call the left table, and matches them with rows from the second table, or the right table, based on a related column. When there isn't a matching row in the right table, the result still includes the row from the left table, but with null values for the right table's columns. This is helpful when you want to see all records from one table along with related info from another, even if some of that related info doesn't exist. The syntax uses select followed by the columns you want. On the left, join with the second table on the condition that links the two tables by a column. The Venn diagram here shows the part of the left circle shaded, indicating all rows from the left table are included regardless of whether they match rows in the right table. A right join returns all the rows from the right table, along with any matching rows from the left table. If there's no match in the left table, the result will show null for those columns. This is useful when you want to keep all the records from the second table, regardless of whether there's a corresponding record in the first. The syntax involves selecting columns and specifying the right join between the two tables, using the on clause to match the columns. The Venn diagram here shows the full right circle highlighted, which represents all rows from the right table being included. Here we want the user to see the total sales for each product color on the sales transaction screen. The example shows a query that groups sales data by color and sums the list price, filtering transactions that occurred after June 1st, 2001. This allows users to quickly understand sales performance per color over a specified time period. The results display the total sales amounts broken down by color, including cases where the color is not specified, which helps provide a clear overview of monthly sales trends for each product variant. A delete statement allows you to remove specific rows from a table. To use it, you specify the table and, optionally, a condition that identifies which rows to delete. For example, to delete an employee with the ID of 100, you would write delete from employee where ID equal to 100. If you leave out the where clause, all rows in the table will be deleted. So it's important to be careful with that. After running a delete command, you need to either commit the transaction to save the changes permanently or roll back to undo them if something went wrong. This gives you control over how the data is modified in your database. The truncate command in SQL is used to remove all rows from a table quickly and efficiently while keeping the table structure intact. Unlike the delete statement, truncate does not fire any triggers, and the operation cannot be rolled back. So once executed, the data is permanently removed. The syntax is simple. Just type truncate table followed by the name of the table you want to clear. For example, if you want to delete every row from the employee table, you would run truncate table employee. This makes truncate ideal for situations where you need to empty a table completely without logging individual row deletions or running additional constraints. The SQL drop command is used when you want to completely remove an object from the database, such as a table. When you drop a table, all the rows it contains are deleted, and the table structure itself is also removed from the database. This means that the indexes associated with the table, as well as any privileges granted specifically for that table, will be deleted too. The syntax is straightforward. You write drop table followed by the table's name. For example, to drop a table called employee, you would simply use the command drop table employee. This operation is permanent, so it's important to be certain before using it, as it removes everything related to that table from the system. When defining a table layout in SQL, you start by specifying the table name, followed by the column names along with their data types. Each column can have constraints such as not null to ensure a value is always provided, and default values that automatically fill in if none are specified. Integrity constraints help maintain data accuracy and consistency, including checks like ensuring salary values are positive. Relational constraints link tables together, such as foreign keys, though they aren't shown here. For example, the create table statement for employees defines an employee ID as a required numeric field, first and last names as variable character strings, hire date with a default of the current date, department ID is a number, and salary is a number that must be greater than 0. This structure is confirmed with the describe command, which lists each column's name, nullability, and data type, providing a clear overview of the table schema. When creating a table, it's important to specify a data type for each column because data types define the kind of values that column can hold. This ensures data consistency and accuracy. The ANSI standard provides a common set of data types that many databases follow, while Oracle has its own built-in types that largely align with ANSI but may have specific differences. For example, an integer or small int in ANSI corresponds to Oracle's number type set to 38 digits of precision. Similarly, numeric types with precision and scale translate to number with those parameters in Oracle. Character data like varchar and char become varchar2 and char in Oracle, respectively. Floating point types such as float and real are represented by number as well. Additionally, users can create their own custom data types to suit specific needs. Understanding and correctly defining these data types is crucial when designing tables, as it governs how data is stored and managed within the database. The union command allows us to combine results from two different tables by selecting related data, similar to how join works, but with some important differences. When using union, all columns selected from both tables must be of the same data type, and the command automatically removes duplicate rows, showing only distinct values. For example, if we want to get a list of cities from both customers and suppliers tables, we use union to combine those city lists into a single output, and we can even order the results alphabetically. This makes union very useful when you need a unique set of values from different sources without any repetition. The union all command works like union, but instead of removing duplicates, it includes all values, even if they appear more than once. In this example, the SQL statement selects cities from both the customers and suppliers tables and combines them with union all. This means if a city appears in both tables, it will show up twice in the result set. The query sorts all the cities in order, making it easy to see every occurrence from both tables without filtering out duplicates. This can be useful when you want a complete list that includes every entry, not just unique ones. Index is a tool used in databases to help find data faster and more efficiently. While users don't see these indexes, they work behind the scenes to speed up searches and queries. You can create a basic index on a table using the create index command, which allows duplicate values in the column being indexed. For situations where you need to ensure that the values in the index column are unique, you use the create unique index command. This unique index enforces that no duplicate values exist in those columns. Both types of indexes help improve query performance by allowing quicker access to the relevant rows within a table. A view in a database acts like a virtual table that doesn't physically store data but is created by running a query that joins one or more real tables. It looks and behaves like a regular table with rows and columns, but the fields actually come from the underlying tables in the database. To create a view, we use the create view statement followed by the view name, and then define the columns and conditions using a select query. This allows us to simplify complex queries by encapsulating them into a single object that can be referenced like a table, making data management and retrieval more efficient. This example shows how to create a view called suborders. A view is a virtual table created from the result of a select statement. Here, the view combines data from the suppliers and orders tables, selecting the supplier ID, order quantity, and price, but only for suppliers named IBM. This is done by joining the two tables on the supplier ID and filtering by supplier name. Once the view is created, you can query it just like a regular table using a simple select statement, which makes accessing this specific subset of data easier and more organized without having to write the full query each time. A trigger is a special block of code that runs automatically when certain database actions happen, like inserting, updating, or deleting data in a table. These triggers are set to activate before, after, or instead of these operations, depending on how they're defined. You create a trigger using the create trigger statement, where you specify when the trigger should fire, before, after, or instead of the action, and which action it relates to, such as insert, update, or delete. You can also define it to work on specific columns, reference old and new values, and apply it row by row. Triggers are useful for enforcing business rules, validating data, or keeping audit trails without needing to manually run extra code every time a change happens. In this example, we created a trigger named deleted details that activates before a delete operation on the TBL customer table happens. For every row that is about to be deleted, this trigger will run a specific function called customers delete. This setup allows you to perform custom actions automatically whenever a delete command is issued on that table, such as logging changes or enforcing business rules. If you no longer need the trigger, it can be removed using the drop trigger statement, which in this case specifies deleting the trigger named delete details on the TBL customer table. Triggers like these help automate and control database behavior without requiring manual intervention each time data changes. Stored procedure is essentially a set of SQL statements that are saved in the database for repeated use. It can accept input parameters, which allows multiple clients to use the same procedure with different data over the network. This helps reduce network traffic because the commands are processed on the server side rather than sending many separate queries. It also improves performance since the procedure is precompiled. Another key advantage is that when a stored procedure is updated, all clients automatically use the latest version without needing changes on their end. To run a stored procedure, you use a command like execute eligible scholar, followed by the needed parameter. This approach makes database interactions more efficient and easier to manage across multiple users. A subquery nested within an outer select statement includes several key parts. First, it has a regular select query with its usual select list components, just like any other query. Then, it includes a from clause that specifies one or more tables or views involved in the subquery. Additionally, it may have an optional where clause to filter the results, a group by clause if grouping is needed, and a having clause to filter groups after aggregation. These components work together within the subquery to return a specific set of results that the outer query can use for further processing or filtering. This structure allows you to embed complex queries inside another query, making your SQL more flexible and powerful.